So today we are going to start a very new topic called wave optics. It is also called scalar wave optics in a way. So what we exactly study in this chapter? So we all know something about light. And so far we have assumed that light is moving in a straight line. So we call it a rectilinear propagation of light. But the wave optics will never talk about the rectilinear propagation. Rather, it will talk about a different characteristic of light. So here we are going to take the wave character of light. We know that light exhibits dual character, which means sometimes it exhibits particle-like character, sometimes it exhibits wave-like character. And based on the various phenomena that we have observed in nature, we cannot or we fail to explain certain phenomena if we only consider the particle character. And similarly, we fail to explain certain phenomena if you only consider the wave character. So it's a very common issue, which is sustained for long time. And it was Einstein who finally said, "Okay, light can exhibit the dual character." So at once, it can either behave as particle or it can behave as a wave. And depending on the phenomena, one of the assumption about light will let you explain the phenomena. So we have something called a phenomena of polarization. Now, the phenomena of polarization we cannot explain if we assume the light as a wave, as a particle character. So particle character never let us explain the concept of polarization. So of course, because one assumption is failing to explain certain phenomena, which is in reality is being exhibited by the light. It means we have to invoke the other model of the light, and we call, okay, let's say the wave like character is also there. But if you only consider the wave-like character, then again we fail to explain certain phenomena like photoelectric effect, like Compton effect. So again, when you fail to explain something, you again change your side and you say, no, the light exhibit particle-like character. So we'll try to understand the wave optics in the context of light, and light will exhibit the wave-like character and particle-like character. We'll see how the particle-like character itself is a wave-like character. And we'll try to differentiate between the particle and the wave concept in context of light. So first of all, we'll talk about the light and how it is developed, how we get the light into reality. So light is an electromagnetic wave. It's a part of electromagnetic spectrum. And when I say light, it means the visible light. I'm talking about the visible light. So visible light is simply a part of the electromagnetic spectrum. Now, if we talk about the wave in context of sound and all, we know that the wave is some sort of disturbance which propagates through the medium. Now, if we talk about the wave in context of light, the medium is not the criteria to explain. So how we explain wave in case of light? So we say that light is an electromagnetic wave, and what it carries is the energy and momentum with the help of self-inducing electric and magnetic field both. So what we can say is it carries energy and momentum with the help of self-inducing electric and magnetic field, which means the electric component of light will induce the magnetic component, but the magnetic component of light will induce the electric component. So in a way, it is the interconversion of one component into the other, which leads the energy to propagate further and further. And this the mutual induction process of electricity to magnetism, magnetism to electricity, it is self-inducing phenomena. There is no need to have any agent to do this. In nature, this happens naturally, and the light propagate because of this very interesting self-inducing phenomenon. So when it comes to light, the way we should see the light in the context of wave is oscillating electric and magnetic component. So we have basically a vector called electric field vector, and this field vector is performing the sinusoidal motion, and not just sinusoidal motion, it is also propagating just like any progressive wave will propagate. So from the wave and sound chapter, you might have heard about the progressive wave. So any progressive wave will propagate away from the source. So what you're looking at here is an oscillating electric field. So this is the oscillating electric field. And I might have discussed that human brain actually interact with the electric component of EM wave, that is the light. Our interaction is with respect to the electric component, and you can clearly see the height of the electric field is representing the instantaneous magnitude. So the height is variable. So we define something called amplitude of wave, which is the maximum height, or you can say maximum displacement. In the context of electric field, we call it E naught. And you can see that it is a time varying field, and it is a field which is propagating in a certain direction. In this case, let's call this X direction. The other component is the mutually perpendicular oscillating magnetic field, and the plane of the magnetic field will be exactly at right angle to the plane of the electric field. And these two mutually perpendicular field we call light. So what you understand by light is actually this. And now you can come back to the chapter of vector. You can understand these are vectors. But the problem is, if you look at these sinusoidal vectors, they keep on varying in magnitude. Okay. They keep on varying in magnitude. And this phenomenon will not stop here. Rather, this will continue forever. And this direction we call B. And the maximum value we can call it B naught, which is like the amplitude of oscillating magnetic field. And perpendicular to both the direction of light is assumed. So we say that the light will propagate in the direction perpendicular to the E and B plane. So the plane which contains E and B the light will propagate in this particular direction. So here the time varying electric field is inducing the magnetic field, and luckily the time varying electric field is inducing the time varying magnetic field, and due to this the time varying magnetic field again induces the electric field. So it is like one is shrinking, other is growing, and other is shrinking, other is growing, and this mutual induction process keep it going forever. And that is why the medium, the requirement of medium is not in case of light. So we are not supposed to have a medium for sure for this light to propagate into space. Now our chapter is basically based on the one of the component, which is I will take electric component. So human eye will interact with E. Okay. Now these are very high frequency waves. So you can imagine that the frequency is so high that even in a one single second, you will actually intercept trillions of waves. So 1 second is really huge interval, and you can actually see an infinite wave reaching your eye. So in a moment that the brain is able to create some perception, so human brain is having some inertia. Not just brain, the entire process of the body is having some inertia. For example, if you see something, the retina will have the inertia to carry the image for the next 0.1 second. Which means if you see something and if the object is not there for next 0.1 second, you can still see it there. Because the brain is having the inertia, it holds something for some time actually. Similarly, we have the persistence of hearing, we have persistence of vision also. And the same thing happens in the persistence of hearing. In the persistence of hearing, what happens? Whatever you hear, the brain will keep on listening to it for the next 0.1 second. And therefore, if multiple things are said to you in the interval of 0.1 second, your overall perception will be the average of all such event which you receive in that 0.1 second. So brain cannot understand something instantly. It takes some time. So there is an inertia to process. I mean, you take some time to process it and understand it. And therefore you have the natural inertia. So whether it comes to vision or whether it comes to hearing, this inertia is always there. Understood? So now this inertia is very, very critical, and it will help us in understanding why the wave phenomena is the way it is. So first of all, we'll try to understand the inertia also in the later part of this chapter. So we'll try to understand what is light. Now, of course, this is the electromagnetic picture of light. But beyond that, we also need to understand how the light is generated, how it is emitted by a source. Yes, go ahead. Go ahead with the question.
Sir, will these two waves always be in phase? Like you have drawn them, they'll both increase and decrease in phase, or will there be a phase difference between the electric and the magnetic component?
No, there will be phase difference. I mean, generally there is a phase difference in general, because one will create the other, so definitely the difference is there in phase.
Okay.
This is how we draw it. This is now it is produced. So at one instant you may see some part of this and some part of this.
Okay.
So we'll come to that also. We'll talk about phase in detail because the phase is the essential concept. And I know that many of you have not actually studied the wave and sound chapter. That's why I'm going to take this chapter in a way that nothing is required. I mean, even if you don't know about the phase or phase difference, I'll take care of it in this chapter itself. So the light, okay, we'll focus on the electric component of light. Okay. At the end of this component, what we have is a line, a vector. Okay. And if I choose a vector, it will have some length. Just call it E. And we know that the maximum length is E naught. But in general, if I pick one of the arrow, it is having different length. Let's say this is E naught, this is E. Now you can see how many length we have. Can you count? How many possible values we have between here to here? Infinite. So how to take care of the infinite values at once? That is a big problem. We want to take care of the infinite values. So we thought of a model like if I express every value independently, it's very difficult. I mean, difficult job. So how we can take care of everything at once? Can you guess? Anyone? Can we really create all these vectors with the help of only one vector?
By using a phasor.
Exactly. So here comes the concept of phasor. Phasor is a very neat technique in which we employ the biggest value called the amplitude and we rotate this value, and after rotating we take the projection, and it is the projection which will give you the other values. So for example, if I draw a circle and if I assume the radius of the circle equals to the biggest value of the sinusoidal oscillation, and if you take that as a radius, then probably we can generate every value with the single line simply by rotating it. So if I call this as E naught, and if I try to project E here, and if you take the projection or the shadow of this line or this arrow over the E line, tell me guys, what is the shadow length right now? What is the length of shadow?
E naught.
The length of shadow on the E line is how much? On the E line, this Y axis. You can see clearly it's 0.
Yes, sir.
So you can just do a ray kind of thing here. We said the light is coming this way, and we'll try to look at the shadow. So what exactly phasor is doing is it is reciprocating the same behavior, but now I do not need multiple lines. One line is sufficient to represent other line. So after, let's say if I draw the same arrow here, I haven't changed the arrow. I haven't changed the arrow. My arrow length is still E naught, but because I have turned by some value, let's call it theta. What is the new value? What is the new projection? This new projection is how much? E naught sin theta. Is this clear?
Yes, sir.
Now see that sine or cos is all about the way I have taken that angle. So if I would have taken the theta from the vertical, I would have got the cos theta. So don't worry about sine and cos because both are symmetrical. They are complementary way of writing. So the beauty of sinusoidal wave is that I can express every possible value of sinusoidal wave by choosing only one line or one vector and then start rotating it and take the projection. So when we represent a variety of lines, see, we are only concerned about the length. I am looking for the length of the vector. And why I need length, I'll come to that. So what I need is the length. And we know that the two consecutive lengths cannot be equal. So if I choose this and this, there is a difference. If I choose this and this, there is a difference, there is a difference, there is a difference. So we have difference in the length. How to express all these differences in a single, I mean, using some simple variable. So we devise a method called phasor. So this is called phasor. A phasor is basically a nice way to call a rotating vector. And what we do is in this rotating vector, we choose the biggest value as our radius because see, of course, we cannot exceed that length. So the radius is the ultimate length, right? So the ultimate electric field value we can get is how much?
E naught.
So can we get more than this? The answer is no, we cannot get more than this. So the ultimate projection what we need is equals to E naught. So every other length will be less than this, and therefore we can achieve this easily by using a rotating vector. So when you take two such lengths, let's say I pick these two lengths, and if I put in a phasor, diagram, what do you expect? If I pick these two lengths and if I put in a phasor diagram, what do you expect? Are they on the same angular position or different angular position? What they represent? Same or different angular position? Tell me, guys.
Different angle positions.
Different angular position. And that is logical, isn't it? You're trying to represent the two length on a phasor diagram. So they will represented by the two different angular position, theta 1 and theta 2. And the difference of the angular position we call phase difference. So now you know what is phase difference. So phase is a concept which we employed for the phasor. So when I say phase difference, I say what is a phasor difference? How these phasors are actually put over a circle. And if you put over a circle, then what kind of difference you will see? Whatever you see is called the phase difference, and it is an indirect technique to actually explain the two line of different length or two vectors of different length, because we can see in this region all vectors are having same direction. They only differ in what? They only differ in length or the height or the magnitude. So because the difference is only in height, and let's say if I want to know what is the sum of these two lengths, if I want to add these two lengths, how to get the idea? So the addition of two vector in a linear scale is addition of two phasor. So every two vector, see, if I want a vector, I can say this is E1, this is E2. Adding E1 and E2 is same as taking the phasor and adding the phasor as a vector. See, both are same phenomena. So if you want to add E1 and E2, and if you want to add these two vectors as a phasor, it will give you the same length. So let's say if you add E1 with E2 and you get a new length equals to this value, the phasor will depict the same answer as the resultant of the two vectors, something like this. Both are same thing. Okay. So phasor is just a technique. It's a mathematical technique. Don't take it, something as a reality. It is a simply technique in which every linear oscillation we project on a circular scale. And when the linear oscillations are projected on a circular scale, we call phasor. And therefore, when we choose two phasor, they will exhibit different angular position on a linear, on a circular scale. And this difference of the angular position we call phase difference. Okay. So even those who are not studied before about the phase or phase difference, they can relate what is phase difference. I hope you have heard at least in your school. So do you understand what is phase difference? Everyone?
Yes.
sir.
Phase difference is just a technique to represent the difference of height on a linear scale by projecting it in on a circular scale. And then because we are trying to project on a circular scale, then every length will have different angular position. And this angular position is called basically what we call we call phase angle. It's like the angle of the phasor. Angle of the phasor, or simply phase angle. But it is so popular that the angle we removed after some time. So now we only call phase. Okay, so phase angle is the complete word. And it is a usage, because it is typically known that we are talking about this angle. So now it is commonly called phase. Don't worry, when someone is saying you phase, you can always create an idea of angle. Okay. Now the question is why the idea of phase is important. See, if you want to add multiple values of E, it is difficult to find the length. Okay. But it is found that the difference of length can be easily understood if we know the difference in the position. So for every linear position, we have the angular position on a phasor scale. So two linear position, if we know the separation, we can exactly know the separation in the angular scale also. So it is like a mapping process. We map the linear separation onto the angular separation, or you can say phase angle, when we project them in terms of phase. So for sinusoidal oscillation, if I talk about only sinusoidal, so for any sinusoidal oscillation, if I call this as anything electric field, or you can say X. For one oscillation, we know that this is lengthwise what we call
Wavelength.
wavelength. So this is called lambda by 2, this is lambda. Okay. And what you can see, what is the length of this oscillation here? 0. And you can see here, it is 0. So if I project these two on a circular scale, if I try to draw the electric field at these two locations, my phasor will be like this and like this. So technically, it will overlap, isn't it? I'm just showing it slightly different. So basically, these 2 points are representing two phasor, and these are overlapping phasor. So we say that the blue line has come to the red line after, actually, if I choose the first as red, if I choose this point as red, and if I choose this point as blue, they appear same, but are they same? Actually, no, because the blue will come after rotating exactly how much?
2 pi.
So what is the angular difference of these two lines, the red and the blue line?
2 pi.
It is on an angular scale, it is 2 pi away. And luckily, anything which is 2 pi away will coincide. It's a sheer fortunate. This is the property of circular scale, that if you make anything turn by 2 pi, it will come back to its original position. Or you can say they will have same phase. So are these two having same phase? Yes or no?
Yes, sir.
Because eventually they are represented on a circular scale at the same angular position, although they are differing by 2 pi. So the third person after 4 pi will also coincide. The fourth person after 4 pi, 6 pi will also coincide. So any two vectors whose angular position will differ by 2n pi will coincide, yes or no? Any two vector having the difference of 2n pi, where n is integer, on the angular scale, will they look like same?
Yes.
So can we say they are having same phase angle?
Yes, sir.
Can we say they are in the same phase? So what do you mean by when you say two waves are in same phase? You mean that they are at a location at which their height and the direction are same. In vector form, let's imagine a vector here. So where are we going to get the similar vector on this sinusoidal wave? I need to extend the wave first. I want a person exactly same as this person. I'll move. Of course, I'll get one here also, but I'm not interested here. I'll move till. Now you will ask, so why not here? Because the very next moment it will shrink. So you see, if I'm here, the very next moment it will shrink. But if I'm here, the very next moment it will expand. Now the behavior must be similar. So if this vector is, if the first vector is moved right, what do you expect? Increment or decrement?
Increment.
Increase.
So the other one should also have the similar behavior, then only they are in phase. So this is not in phase with this, because if the left vector will move right, it will expand, but if the right will move right, it will shrink. You can see. Try to understand the animation. But if I am here, then the two vector will exhibit exactly same behavior, isn't
Yes.
it? Now, definitely, if I try to project the first on the circular scale, it will not be occupying the horizontal position, rather it will have some position which we are not aware of. So on a circular scale, how you are going to depict the first one? Can we represent something like this?
Yes.
Yes.
With some angle, which I don't know how much. And okay, I'll change the color just to understand. And if I want to represent the red one on the same circular scale, how it will look like?
Coinciding with it.
It will again coincide. So what you can understand here, that these two vectors are having a position which differ by lambda again. The lambda is not a crest to crest or trough to trough. Lambda is basically defined as the separation between the 2 points of a medium, at which if you go, you will get two vectors of exactly similar character. They are in phase, guys. Okay. So what is the definition of lambda? Lambda is the minimum characteristic separation between 2 points of medium at which the wave oscillate in same phase. In a way, if you project on a circular scale, you will get the similar angular position. And it is a minimum separation. So lambda is not crest trough, something like this. Lambda is an idea. It's a concept that, okay, if you are walking in a medium and if you see some guy dancing there, exactly how much you need to move to see a exact person dancing in a similar fashion. And because it's a periodic or rhythmic dance in which things are getting repeated again and again and again, so we can expect a similarity of the event at a regular interval, and that regular interval we call wavelength. So we do not have something really wavelength. We don't have length kind of thing. It's an idea. And this idea will stick with any sinusoidal wave. Okay. Or any periodic wave. And of course, for wavelength to be defined, it is necessary that they have the behavior which is repetitive in nature. And of course, we need not to have the sinusoidal. We can have any shape of wave, but that should repeat the process. We should get the similar fashion getting repeated again and again. So for any periodic wave with a shape getting repeated, we can expect a definition of lambda. If there is no repetition of shape, the lambda is meaningless quantity. Okay. So I hope the idea of phase is clear. Those who are studying for the first time. So what you can see that a phase difference of 2 pi is equivalent of path difference of lambda, isn't it?
Yes.
Yes.
So 2 pi phase angle difference, I'll write everything completely. 2 pi phase angle difference is equivalent of, I'll write on this side, lambda path difference is equivalent of, equivalent, I'm not saying equal, equivalent of 2 pi phase angle difference. Yes or no?
Yes.
So
Yes.
what is the unit path difference equivalent of? Unit path difference
2
is
pi by
equivalent of
2 pi
2
by
pi by lambda phase angle difference. Is this correct?
Yes, sir.
And now the
Yes, sir.
beauty is, if I choose any two random point with the delta x separation,
2 pi lambda into delta.
correct. So then the expected phase angle difference. So for every 2 points in a medium which are well separated by delta x position, if you try to plot their phasors, then the angular difference between those phasors will be equal to how much? Try to read this carefully, what I'm trying to explain. This part is
This
crucial.
is the path difference, no?
No, this is the path difference. This is the corresponding phase angle difference.
Okay, okay. Huh.
Do you realize this?
Yes, sir.
Yes.
And that's common sense. It's like I can understand mentally that on a medium which is well separated by delta x, if you go and see vectors present there, and if you try to project those vectors on a circular scale, what kind of angular difference you can expect? 2 pi by lambda into delta x. That's why for every delta x, there is well defined delta phi, what we call delta phi. So the delta phi is a way to write the phase difference, and phi looks or sounds really nice. It's phi phase. So we will stick to this good sounding notation. There is no biasness towards the notation. You could have used delta psi and I would not have complained at all. Or you would have used delta, really bad angle delta, and it is still okay. Or delta alpha. I mean, no one is there to stop you to choose a symbol of your choice. I will stick to symbol of my choice. Yeah, not my choice. It's a choice by many authors. So I will just cut, copy, and paste their choice, and will declare as my choice. So the delta phi we can write as delta phi. We can write as 2 pi by lambda into delta x. And because in the chapter of wave and sound or in optics, this term appeared so many times that we got bored of writing 2 pi by lambda, 2 pi by lambda. So people thought, let's put this into a perspective, and they define a new hypothetical quantity. They called it k, and k is called, what k is called? They have given name angular wave number. So it is simply that they got fed up with writing 2 pi by lambda. Nothing, there is no other idea of k. So instead of writing 2 pi by lambda, 2 pi by lambda, they created a symbol. And why they called angular wave number? Because we know wave number. What is wave number? Inverse of lambda. Which means how many wavelengths are present between in 1 meter, right? Number of wavelengths, you can say number of wavelengths present in 1 meter. Because it is 1 by lambda is linear wave number, and because we introduced 2 pi, so it's suitable to call angular wave number, though there is no physical meaning associated with it. So this is totally a fake physical quantity developed for those lazy writers who do not want to write this 2 pi lambda again and again. So, okay, anyway, I think most of the physicists and engineers are lazy nature and they do something like this. Okay. So imagine if you look at the various laws of electromagnetism, which we study in class 12, we express Gauss law and other law in integral form. And then someone called Oliver Heaviside developed the differential notation, which is quite shortcut. Again, it's a lazy work. And the biggest, laziest work that ever happened in mathematics is called tensors. So tensors notations are actually meant for represent something really compact. It's a very verbose at the same time into simple notational symbol. And that's how the Einstein was able to express his general theory of relativity by designing some nice symbols. So to understand mathematics, you need to understand what exactly went into the mind of those mathematicians and why they developed those notation. So notation will have its significance. It brings a lot of abstraction into picture. So I hope the phase difference should not bother you. Okay. The phase difference should not bother you, isn't it? They are having a very simple relation.
Yes.
So for every oscillation, or you can say sinusoidal wave, the height of the wave at any instant can be related with the maximum height. So maximum height and this particular height, how we can relate? In terms of phase angle, right? So maximum height is what? E naught, which is like a vector radius. Okay. And the projection height is the instantaneous E value. So let's say the blue line is at some angle theta and the maximum is at what angle? 90. Where you will get the peak value? The shadow length will be equal to the maximum height where? When angle is 90 degree, right? At 90 degree, the shadow will become as big as the actual vector. And that will happen at 90 degree. So the whole idea of phase is a method of, a convenient way in which every height can be accommodated using a single variable called angle. And in the context of phasor, we call phase angle or simply phase. So these are all literature, a beautiful literature written to make it easier to understand. So I hope the idea of phase is clear to all of you. If you have any doubt, you can ask, because this is the most crucial part of this chapter. Rest is nothing. I mean, this chapter is over by this topic only. The rest is some cosmetic changes. I'll explain what are the cosmetic changes. The phase idea is clear to everyone. Okay. Now after this, okay, we had talked about light. We will come to something called mechanism of light emission. So how light is emitted, anyone?
Light is emitted.
How the bulb, tube light or whatever LEDs, how they are emitting light? The only phenomena by which light is emitted is called the electronic transition. There is no other way to emit light. Okay. So no matter which physical object you are using, the core of light is the electronic transition. We do not have any other mechanism by which light can be generated. So we know that in atom we have orbits and every orbit will have different energy level. So whenever any electron will transit from the high high energy orbit to the low energy orbit, in accordance with the Bohr's principle, the difference in the energy level will be emitted as photon, or simply you can say it is a single pulse of light. So light is essentially collection of a small pulse, and these pulse we call photons. If you have heard this name before, you can correlate that a photon is basically a single pulse that a single transition generates. Okay, in this particular guys.
Yes.
So no matter how big the source is, no matter how big the source is, the mechanism of generation of light is simple. It is the electronic transition. Okay. So if I take some physical source, then in a physical source, how many atoms we have? Can we count?
No.
The answer is no, we cannot count. So we have simply infinite number of atoms. And can we really control which atom will undergo which kind of transition?
No.
No. Can we really control that which electron will jump when?
No.
And that is the biggest problem with the light. In a reality, we have no control over the way light will be emitted. I mean, of course, the phenomena is fixed, it is transition, but we have no control way like when all of them will jump together. Will they jump together? If it is Olympic race and if I shot the bullet, they will start running. Can control similar to that? That I'll control every electron that okay, no, wait. When I'll say 1, 2, 3, you all will jump together. Imagine if you can really do something like this. If you can really control that every electron will jump together, then that will lead to something called the monochromatic light. But in reality, we never control. So we have a method called the laser technique. And the laser technique actually employs the same phenomena. In a way, it controls the jumping phenomena. It controls that by creating some meta state. Apart from the stable orbit, they create some meta orbit. And what they do is they bring all of them to that meta state and they let them jump together. And when they jump together from that meta state to a ground state, they are able to create light amplification by stimulated emission of radiation. We stimulate the atoms, we kind of provoke the electrons to go to meta state. And once they all reach the meta state, we call something called population inversion. So the majority of the electrons are in the meta state and then they jump back to the ground state. And when they all jump together, they create a single wavelength as a collection of large number of pulse or burst. And that collection of photon which are jumping together, we call it laser. So laser is a way to create a close to monochromatic light. Because in atom, a single orbit will have multiple energy levels. If you know the suborbit, I mean, you can say orbitals. So every orbit, if you expand, it will also have the range of energy, isn't it? So if I zoom this portion in a way, technically, it is like a band actually, energy band. So again, when I say the electron is jumping from one orbit to another orbit, within the orbit itself, we can have multiple energy levels. So if we say that an orbit is containing a large number of meta states. So by making all electron reach a same meta state, will make sure that we have similar energy difference, and the similar energy difference will lead to similar wavelength, and that will lead to the close to monochromatic light. So in reality, the light is not monochromatic. What we call is quasi monochromatic. So quasi monochromatic means close to monochromatic, not exact monochromatic. Our endeavor is to achieve as close as possible. And some time ago, a Nobel laureate won this prize for the creation of blue laser. Now the blue laser is already in place, but not as monochromatic as he got. So he was able to create a material in which the method of achieving the meta shed was quite easy, and he was able to create a extremely monochromatic wave. The applications are infinite. I mean, you will come to know the application of why we need really such a monochromatic light. To study various, you can say, phenomena, we need this idea of monochromatic light. Why does that matter? But can you explain the question, Adar?
So when you were talking about controlling, like jumping,
Yeah, we
so I
cannot
was
control.
asking why that matters. Like why do we
Yeah,
need to
yeah,
jump?
yes, yes. So every light which will jump together will move together. So once the light is developed, light will propagate into the space, isn't it?
Yeah,
So if all we jump together, they will leave the matter together. And if they leave the matter together, they will go further together, isn't it? And they all will reach your retina together. Yes or no?
yeah,
Now, what if now see the once the photon will hit the retina, it will not wait there for their friends to come. It's gone. The event is over. Every next instant, you receive a different set of photon to see the same image. So while you are looking at this monitor, every nanosecond, you are looking at the monitor with the help of a different set of photons. Do you realize this?
yes, sir.
One set of photons is letting you see this monitor for only few nanoseconds. In after 10 nanoseconds, you are getting a next burst of photon reaching your retina from the same monitor. This monitor is constantly emitting the photons, constantly. Okay. So now the photon which you have received now and the photon which you will receive later on, can they interfere? No, because one is gone. The moment the photon will reach your retina, it is gone. So its existence is lost because that energy is completely absorbed by the cells of the retina.
So,
Yes.
sir, these photons have like very high momentum and energy. So, like,
Yeah.
they disrupt the retina or something, or
Of course, because of that only the retina will oscillate as a dipole because it is high frequency wave. So when it will reach the retina, it will also set the dielectric of the retina into oscillation by the induced dipole moment.
yes.
And it is the oscillation of the dipole creates the idea of color. So cones are actually getting oscillated by the same frequency as that of the incident electric field. And because there is a match of frequency, the brain will kind of imitate that color. Color is the brain way of coding something frequency. So every frequency is coded in terms of color by the brain. So you can say frequency is a mathematical thing and color is a physiological event. So your sense of color is the brain way of understanding that physiological event. I mean, this is one event which is mathematical and other the brain way of doing it. So the color is an idea for the brain to understand or distinguish various frequency. Understood?
Yes, sir.
Okay, it's really deep. Don't go into it. So Now the mechanism of light emission is clear. Now why it really matter? What I said is every electron which is jumping together will propagate together. So it is depicting a generation of photon, one generation. So in case of matter, the light coming, when you talk about 1 second, in 1 second light can travel how much? 3 lakh kilometer. Can you imagine? 3 lakhs kilometer in 1 second. So 1 second is huge. Imagine two wave bursts at 1 second separation. How far they will be? How far? 3 lakhs kilometer. Now, do you think that two waves at 3 lakh separation will interfere? Come on. It is like you're saying that a person will marry a person which is 500-year old. I mean, that person doesn't exist. Come on. They cannot marry each other. So the interference, or which we call superposition, is a phenomena which only happens between similar generation. And so it is essential that they must be born roughly together, if not exact together. And that is how the idea of interference came to picture. And that is how it is so difficult that a natural light can interfere. A natural light is a composition of infinite generation. And because of the infinite generation, they do not interfere. Or even though they interfere, we cannot understand. The problem is, if you really want to superimpose two waves, we have to somehow make sure that they born in the same era. The creation happened at the roughly same time. Okay. It means they are the byproduct of all those electrons inside all those atoms, inside all those matter, which roughly jump together. Do you realize this?
Yes.
So there is the idea of generation. Now, this idea of generation of photons was well structured by, and much before the photon idea was actually present. So Christian Huygens, he developed the idea of wavefront. So what is wavefront? So we'll talk about this in detail. So wavefront is exactly that idea, that one wavefront is actually one generation. So you can say it's like an envelope, a two-dimensional space, and that two-dimensional space is occupied by all those photons who were born in the same generation. Understood? So when light is emitted, it is left by, a photon is leaving the source. So after leaving the source, it will not wait, it will propagate, right? So who all will propagate together? Those who are born together. And who all are born together? Those who jump together. Do you understand this part?
Yes.
Generation. So the mechanism of light emission is the crucial way to understand the concept of interference. Interference is not possible between two different generations. So if we have a light belonging to two separate wavefront, can they interfere?
No.
No. If light belongs to two separate wavefront, it means they belong to two separate generations. And there is no question of interference of the two generations. Only one generation people can understand each other because they have similar mindset. And that's why we call the generation gap. Okay. So generation gap means, okay, they fail to understand each other. There is a less understanding. And there's a very nice or technical way of saying it in physics. We call they are incoherent. And we have a term called coherence. Coherence. So the word coherence has come from the word coherent. And the coherent has come from the word coordination. So in a way, when I say two waves are incoherent, I say they do not coordinate well. They are very bad at coordinating with each other. And if they fail to coordinate, they will definitely fail to interfere. Their thoughts will never meet each other. So their thoughts will be different. Now, in terms of physics, which you, because we are learning wave optics, when I say coordination, it means we cannot predict their phase relationship. I have no idea at what angle you are. There is a lack of coordination. So there is a lack of understanding that what is the phase difference between the two wave belonging to two different generation or two different wavefront. We have really no idea how to relate them. So even though I know the difference of path, can I really write the difference of phase for two wavelengths from two different generation or two different wavefront? Yes or no? So the whole idea is, even this relation in the context of wave optics is only meant for one generation. A small difference is tolerated. So we have some difference. So we have like something called coherence time. What is coherence time? For this duration, everyone born with this much duration, this is the upper limit of the gap of the age. Let's say if you are someone is called millennials, so they are born 2000 and plus. Okay. So anyone, let's say born from 2000 to 2005, we can call all the millennials because 5 years is not a big difference. But 2000 and 2015, they are different generation because there's a decade of difference. So some difference is tolerated. So in case of light, the maximum difference of birth or the light emission that we can tolerate is called coherence time. And we write as TCOH, coherence time. Okay. So it is the duration in which the light will have a chance to understand each other. So we say that it is the duration in which light waves will have somewhat predictable behavior. It means I can predict each other behavior. I can predict the phase. If I know phase of one, I can answer the phase of other. So the ability to predict, it's again a kind of probabilistic idea. So the ability to predict will only exist for the coherence time. Beyond that time, the ability to predict will fail significantly, or in a way we will stop predicting. So if I just want to explain what is coherence time, I'll say it is the duration over which light waves will have predictable phase relationship. Okay, that is called coherence time. Every wave, every light will never interfere. Interference is a phenomenon within a generation. So those who are born together will interfere eventually. Therefore, the idea of wavefront is very crucial to understand. A wavefront is representing, it's a locus, a point at which the wave oscillating same phase. Just Okay. So I hope the mechanism of light emission is clear, how the light is emitted. The idea of coherence time is clear. We'll talk about the coherence very soon.
Yes, sir.
Now, because every orbit will have many meta energy state, so can we expect that every wavelength emitted for the same transition of the orbit will have same wavelength? Or will there be some sort of gap or some sort of difference in the wavelength?
There may be small differences because of the meta states.
Yes, because of the meta state, there will be small differences, not much difference. So can we get exactly one wavelength or collection of wavelengths for every transition?
Collection.
So we never get one wavelength. We always get a collection of wavelengths, and this collection of wavelengths will vary in time. And therefore, this collection of wavelength will superimpose with each other and will give you a nice spread of wavelength. So this nice spread of wavelength around some mean value, lambda, and we have lambda plus delta lambda and lambda minus. So it is almost impossible to get exact one wavelength. We always get a spread, although the spread is very small. And this collection of wavelength we call photon. You can see a photon is basically not a single wavelength. It's again collection of wavelength. Okay. And why we call particle? Why we call particle?
So,
You can see, yes.
sir, so is the energy associated with that photon the average energy?
Yeah, correct. It's always average.
So,
It is never the exact energy. So we always take the mean value, and we explain the energy corresponding to the mean value. This is the lambda. What you call lambda is the lambda average. Okay, the mean value of lambda. What we need to understand that a photon is also a wave. Now, what Einstein said, when I say a particle in context of wave, what I really mean is confined energy. My energy is very much confined within a small tiny volume. And how tiny is this volume, you cannot imagine. So even if I put a dot, it's like a big insult to the tiny volume, because this dot will have the infinite, simply trillions of photons. So we cannot really understand the dimensions. It's so small. So for visible light, we know the dimension. So we know the wavelength is roughly 3800 angstrom up to 7800. This is the mean value of wavelength for various color. Yes, go ahead.
sir, it was like Einstein said just for photons, then that De Broglie said for all particles, no, like any matter.
No. De Broglie said something different. He said that if we have a particle, but if you try to observe a particle which is moving really fast, you won't be able to get the exact location. There is always uncertainty. So the uncertainty of even a particle we can express as a wave-like character. Wave is like a spread. Wave means something which is delocalized, and particle means something which is localized. So every moving object will have some certain some degree of delocalization. Okay.
Sir, but like before this statement, someone had to say na like that all matter have dual nature, not just photons.
All,
Every matter, like all particles are waves and vice versa.
of course, see, I'm not saying things in chronological order. I'm saying things in a way now, which is the way today it is established. I mean, the past sequence I'm not following, like who said first and who said later on. But
Okay.
yeah, every matter will have wave-like character for sure, and every wave will have matter-like character. And to understand the two characters, you have to understand the idea of localization and delocalization. Okay.
So, sir, Einstein just for photon, na? Not
No. Einstein said for the localization. The localization of energy is called particle.
okay.
So when I say particle, I do not mean some pebble or some fine grained sand and something like this. No, the particle here means the localized energy format. When energy is in a localized format, we call it particle. So you have to be very careful with the idea of particle. The particle itself is a very complex concept.
Yes.
So what is particle here? Energy confined. Okay. Written here. The confined energy in a very tiniest possible volume, we call it particle. I hope this is clear.
Yes.
So
Yes.
someone said yes. First raise your hand, then say something. Yeah, tell me. Okay, I hope the particle concept is clear.
Yes.
Okay. And see, because of this particle behavior of light, the interference become really difficult because the spread is not everywhere, it is confined. So when the two photon will interfere, let's say one photon is representing one generation, when they will interfere, can you guess? When the first photon and the second photon having some overlapping region, then only the interference possible. So this spread is actually representing the speed of light into the coherence time. This is how we express. The speed of light into the coherence time is called the spread for which some sort of overlapping is possible, and this length we call coherence length. What we call coherence length. So we have something called coherence length. LCOH. So it is a maximum possible separation for which we expect some sort of what? Interference. If the two wave front, sorry, not two wave, if the two wave having separation of more than the coherence, they will fail to interfere. So it is the maximum possible, you can say maximum possible path reference for which interference is possible. Understood? So if you have a window at home, so window is also like an aperture and light will enter from the window. Now the light entering from the top of the window and the bottom of the window, even they though meet together, they will never interfere. Why? Because their path reference is just beyond imagination. It is infinitely times bigger than the coherence length. Infinitely bigger, I'm saying, infinitely bigger. So to create the coherence, to create the superposition of light wave, the biggest challenge is to create the two small source with very, very small gap. And that is first of all achieved by the Young's double slit experiment. The whole idea was to make sure that even though we have two slits, they are close enough to match the coherence idea. Understood? So
Yes.
the coherence length is the minimum, you can say maximum possible separation for which we consider the event of interference in light. See, the interference of light is very, very difficult task. That is why in real life, we do not see interference of the white light. It hardly meets the condition. Okay. So that's why we need to design a method to make this happen. And this method was, of course, designed by many, including Young. So Young's double slit is a method to create the two waves which can interfere. It's a situation in which the interference is going to be possible. So that design was the possibility of interference, and it was successful. So now we study a lot about the double slit experiment. So I'll talk about something more deep, something called a mathematical wave. So real wave versus mathematical wave. Both are continuous function. Both are continuous. But the problem is the domain are different. So one is having finite domain. So I'm talking mathematically. So finite domain is the spread is very small. It's a finite. So basically we say real waves are localized waves. Localized. The mathematical wave is having infinite domain. It is spread throughout infinity. And therefore, it is always delocalized. In case of mathematical wave, interference is possible for any length because it is everywhere. So if it is unending, so if you represent wave like this, no matter how far the second wave is, they will interfere because they are infinitely spread. So the idea of coherence and all will not exist. Okay. And that is precisely the idea of sound wave. So sound wave belongs to the close to mathematical wave. And that is why in case of sound wave, we never talk about the coherence length, coherence time, and so on. Now the light is real wave because of the way it is emitted. So the mechanism is well defined, and I have no control over the mechanism. Mechanism is something that it is quite not in control. So the real waves are localized wave, and because these are localized wave, the interference becomes a luxury. In a way, it's a very elite process. So for interference to occur, we have to set lot of condition, and if all conditions are met together, then we can think of the interference. Understood?
Yes.
And if you remember that every light, if I remember every light which we represented, I'll come to this concept again in later chapter also. If I consider light, and if I only focus on the electric component of light, one photon will have one plane of oscillation. Can we really explain the plane of the other photon? Or can we expect it must have same plane?
No, we can't.
So how many planes are possible for if we have infinite photons?
Infinite.
So can we say every plane is equiprobable event?
Yes, sir.
Every plane is equiprobable. So when you get a light from a source in which the wave can occupy any possible plane, then such a wave we called unpolarized wave. There is no plane of polarization. It is unpolarized because every plane is equiprobable. So that is the whole idea of unpolarized wave. So white light is unpolarized. Understood? And because every plane is possible, so the electric field can have any direction of oscillation. So to represent unpolarized light we represent by two mutually perpendicular lines. This is the symbol chosen for the unpolarized light. Now, why I'm saying this? Because the problem with the interference is even if you have two separate plane, they will never interfere. So one in this plane, other in this plane, although they're born in the same generation, but if they are not having the same plane, again they will not interfere. Understood? So imagine a person is going in a submarine and other person is on the airplane. The chance of collision is really less until the plane submerges in the the ocean. Similarly, in case of a unpolarized light, if the light is it is not polarized, or you can see if the light we have is having two separate plane, they will never interfere. So for interference, we need plane polarized light. We need PPL. So again, this is the next concept for interference. We need plane so light is having so much tantrums, to interfere, they will show off all the tantrums possible. Are you meeting the coherence length, coherence time? Are you plane polarized? If you say yes to all, then okay, I'll interfere. I mean, they have so much tantrum. Can you imagine? And not only that, the biggest tantrum is they must have the predictable phase relationship. It means if you know the phase of one, you can predict the phase of other. The other way is the phase difference between them must be constant. It should not change. The phase difference should not change. See, the difference is okay, but that should not change. I'll come to this why the idea is so important. So the idea of continuous wave is called wave train. And the idea of it is called wave burst. So light propagate as burst, not as a train. It is always a collection of bursts. So one burst, some gap, another burst. Now this gap is really small because we have infinite photons. And because of these gaps are so small, basically compared to this length is, if I say this is A, this is B, so A is much bigger than B. This is too much, so I'll and therefore we can represent like this. So even the burst will appear as train, but they are like discrete values. We need to understand discrete values. Okay. And it is because of this discrete value, we have variety of wavefront. Okay. So now I'll define something called wavefront. So what is wavefront? Okay, before wavefront, we'll define. What is coherence? It is the coordinated oscillation of wave such that they maintain predictable phase relationship is called coherence. So you might have, I mean, seen or might have experienced the wave formation in the cricket stadium or football stadium, the human wave. Have you heard the human wave?
Yes, sir.
At least seen somewhere in the movies or somewhere.
Yeah.
So what is human wave? What exactly is that human wave? I mean, are they communicate with each other? Okay, you stand up, I'll sit down. Or the coordination is natural.
Natural.
So those coordinations are very much natural. They don't see each other, and that is why, because of the natural coordination, I can exactly say that after what time which person will stand up. If my calculations are very correct, I can guess the wave rate formation, at what rate one person is sitting and how the wave is traveling forward. So knowing the wave speed, the way the wave is traveling, the disturbance is traveling, by knowing the distance of the person, we can really predict the nature, isn't it? So their phase can be predicted, and that is why I'm saying the formula delta phi equals to 2 pi by lambda, we can only write for those waves which are oscillating in coordination. Can we write for the person, I mean, for the situation when the waves are not in oscillation, not in coordination? Can we write this formula? Can we write? Common sense. I mean, just because I know that you're also dancing, I cannot tell you whether you will jump or you will sit down and will do something. Okay, what is happening right nowadays, very common. So the delta phi equals to 2 pi by lambda delta x is only possible to write if the waves are already in the coordinated fashion. I mean, they're oscillating in the coordinated fashion, which is a way of saying that they are coherent. Okay, so if the waves are coherent, then these kind of ideas or mathematical relationship will exist, and we can use it. So coherence is very, very crucial, you can say, step in the learning of interference. Okay. Now there is a way by which we define the coherence length and coherence time. So it's a very standard definition. So coherence, I'll just put a formula for the sake of writing. Coherence length. So we know the C equals to F lambda. For any wave, the speed equals to frequency into wavelength.
Yes, sir.
Or you can say lambda upon time period, but I'll choose this one. Okay. So we know that this is C equals to F lambda. So if I differentiate it, what I'll get? 0 equals to delta F by F plus delta lambda by lambda equals to 0. So what is delta F? So delta F equals to minus F delta lambda by lambda. Am I right?
Yes, sir.
So the coherence time is defined as inverse of frequency interval. Okay. Why mod? Because the time cannot be negative, so I will take mod. So what I'll get is inverse of this is lambda by, and I can replace the F by C by lambda. It looks nice. So this is called coherence time. And therefore, the LCOH the coherence time, or sorry, the coherence length is called C into and it turns out to be lambda square by. So you can see that the spread of a wave burst actually decides the LCOH. So the delta lambda so here you can see the coherence length is depending on the how monochromatic the light is. So if a light is exactly monochromatic, what will happen? Delta lambda will be 0. So for exact monochromatic, delta lambda is 0 and the L coherence is infinite. It means if we can really create the monochromatic light as good as possible, then interference can be seen for any path reference. But in reality, we cannot create exact monochromatic light, and therefore experimentally it is found that there is always a spread and there is always a finiteness of the LCOH. The coherence lengths are always finite. Of course, this is a very advanced topic. I mean, not required to us to understand. And you can totally ignore it. It is not at all important. What is important is the condition. So what are the condition of interference? We have discussed all conditions one by one. Can we put into words? What are the all condition of interference?
Light will be plane polarized.
Yeah, that's correct. So we'll start with the first is the two waves must be coherent. And the coherence is only possible when they have same frequency. Why same frequency? If you remember the phasor, idea, the diagram which I drew, what is frequency? So how much time it take to complete one oscillation? Okay. So imagine if I choose two separate frequency. So let's say the two waves are in phase at some instant. And the one is moving with angular frequency omega, other is also omega. If frequency is same, then they will turn by same value in the same time, isn't it?
Yes.
So the angle turned by both of them will be same,
Yes, sir.
which means the phase difference will be still same.
Same.
Now imagine if one is omega 1, other is omega 2. If this is theta, this is theta 2. So what will be the phase difference between them? Can we say omega 2 minus omega 1 into t? Or vice versa? Which means the phase relationship will become function of time t.
बट यहाँ पे कंडीशन होगा कि दोनों सेम पॉइंट से स्टार्ट किए होंगे, राइट?
I mean, of course, I can take some initial phase also. So if I choose something like this, imagine a situation here very carefully. If someone is here and someone is here. So when you represent by some angle in the very beginning, we represent this by something called phi 1, phi 2. What is phi 1, phi 2? We call initial phase before the motion is started. So what we call is the phase that we saw in the beginning, initial phase. But if I keep the omega same, okay, what is the phase difference between them right now? So phase difference at in the very beginning is how much? Let's call it delta theta.
Right to minus 5.
Now, if the omega we keep as same, so after time t, both will turn by how much? So this will turn by omega t. This will also turn by omega t. What will be the new phase difference? Tell me. What will be the new phase difference?
Still the same.
It's still the same. So having same frequency will maintain the phase relationship between them, and that will not vary with time. Yes or no?
Yes, sir.
So the whole idea of same frequency is that the phase relationship should not vary with time. Why? Why it should not vary with time? Because when the light wave will be incident on the retina for one particular angle, let's say if two vectors are superimposed, superimposition means simply addition of vectors. Basically, you can think as an addition of vectors. So if you add two vectors, they will have a resultant based on the angle between them. Yes or no?
Yes, sir.
So the whole idea of a resultant vector. So retina will perceive the first vector, the second, or the resultant. What retina will perceive?
Resultant.
So if you make the theta variable, what will happen?
Resultant will vary.
It means the retina will perceive different brightness because the intensity is basically proportional to the square of the amplitude of resultant wave actually. And intensity is the mathematical term which translates to the physiological perception of brightness. So imagine if your brain records brightness and dullness both at a very short duration. What brain will perceive? If continuously I am giving you some bright picture, some dull picture because the theta is changing, and so after some time it is quite possible that both will be opposite to each other. We will have minimum resultant, we will have maximum resultant, all are possible. So what I'm trying to say that a brain can only record the average perception. Our brain is only able to say on average. So if you give me infinite values from 0 to maximum and 0, in the duration which I need to process the information, and because my brain can only store the average information, so it will never record maximum or minimum. It will say it's a uniform. In a way, it will never give you the sense of interference. Are you getting this deep point? What is I'm saying? The brain only records the average phenomena, not the instantaneous phenomena. So as I said, we have some duration to process the information. We take some time. And what we define sometime as the inertia. So the brain will have some inertia. It will process the information and will stick to that information for a duration. So if in that tiny duration, if I give infinite values ranging from 0 to, let's say, +1 to -1. So what is the average average perception? What is the average of -1 to +1?
0.
It is 0, which means it will never report interference. Your brain will never report interference. You can say retina will give infinite signal to the brain, and at the brain will say there is no interference, and we end up saying that the sources are incoherent. What do you say? Sources are incoherent, which means their phase difference was not constant as time progresses. So the first rule of interference is, of course, the wave must be coherent. They must coordinate in a fashion. And that is only possible when they have same frequency. So interference cannot be possible with the two different frequencies. Do you realize this?
Yes, sir.
Now, when I say interference is not possible, I should make it very explicit. I am talking about a spatial interference, not a temporal interference. Because if you know the sound chapter, we do have interference of two slightly different frequency. We call it beats. Yeah, beats is also interference. In fact, the more generic term for everything is called superposition, and various names are given based on the various mathematical situation or context. So in one context we call interference, in other context we call stationary wave, in other context we call beats. But at the end of the day, under the hood, it is all superposition of wave. And different distinction given to them is just for the purpose of study. So when I'm saying interference, I'm of course looking after some mathematical context. And if those mathematical contexts are not met, I will not say it interference. Is this clear, guys? The lack of interference creates uniform illumination. So that's why the light entering from the window gives you the uniform brightness as it spreads. But when the light enters the double slit or on the double slit experiment, then it gives you the pattern of bright and dark fringes. So there is a spot of bright region, there is a spot of dark region or dull region. And this dark and dull pattern we call interference. So I'm sorry, bright and dark pattern we call interference. And the brightness is saying that it is the location or the region in which the interference was quite like addition. And the darker is saying that, okay, the interference was quite like a subtraction of vector, you can say destruction of a vector. And therefore we have name like constructive and destructive interference. So definitely we can say the constructive is when theta is like a 0 and destructive is when theta is like pi. Okay. So we have all sort of interference from 0 to pi. We only talk about the two extreme cases. The in between will fall in between these two extreme cases. So for interference to take place, what are the conditions that we must understand? The phase difference should not change with time. The delta theta should not be a function of time. How we can achieve this? Only when omega 1 is equals to omega 2.
Yes, sir.
Yes, sir.
So we must write here, which is, I mean, see, the second line is the consequence of the first line, but still I write as separate, condition. The two waves must have same frequency. What is the third case? When you choose two sources, and if the light is arriving at a point from the two sources, because see, interference is always observed at a point in space. Okay. So your retina is the ultimate screen on which you actually see the interference. So when light is coming from two sources entering your eye and eventually at the retina is the perfect screen on which they will interfere. So if the two sources are arriving, so in a way I can say two photons are arriving. And imagine that they are arriving from two separate sources, and unfortunately they belong to two separate wavefront, two separate generation. Even though they reach together, will they interfere?
Can you repeat?
There are two sources, let's say imagine two distinct sources. and they create a wave which lie on two separate wavefront, and when it will eventually enter the eye, reach the retina, they belong to two different generations, and therefore although coming together, will they interfere?
I don't think so.
They will not interfere because they don't have the predictable phase relationship. The whole idea of interference is that they must have the, because see, when I say interference, I talk about some mathematical event also. So interference is only possible if the path difference, like the distance traveled by the one minus distance traveled by the other, if the path difference, and I'll put a prefix after some time called the optical path difference, because path difference is kind of confusing. So when the optical path difference of the two separate paths exceed the coherence length, we do not assume interference. Once again, if the path difference, optical path difference of two paths exceeds the coherence length, we never assume interference. Is this clear?
Yes, sir.
So what we say is the path difference must be, path difference means, I'll just put as a prefix optical path. See, the geometrical path difference doesn't matter in case of light. Light only understands the optical path. So if the optical path difference must be less than the coherence length. If it is happening, we can think of interference, else forget about interference. The fourth, what was the fourth condition which you said in the very beginning? The light must be
In
plane polarized. So you can see the light throws so many tantrum. It's not an easy task to interfere light, and that is why it was like quite a big challenge to create a setup in which this can be achieved. Okay, so this was the issue. It was the biggest issue actually. So coherent. Now, if we talk about the amplitude, do we need the two circles of same radius, or different radii circles are okay?
They should have same radius.
So is it possible for two wave to interfere if they are born in the same generation, but one is taller, other is smaller? What is important, generation or the height of the generation?
Generation.
Exactly. For interference, the magnitude or the amplitude of wave doesn't matter. They can be equal, they can be unequal. Because that is not a criteria for interference, isn't it?
Yes, sir. Generation matters.
What matters is generation, not the height. Okay, so I can say here. Okay, this is just a very minor, you can say mild point, that just for your understanding. Amplitude doesn't matter. So amplitude may or may not be same. Now, what is the effect of may or may not be same? If they are exactly equal, then two vectors will exactly cancel. And if they are not exactly equal, then the cancellation will be non-zero.
Non-zero.
Which means the perfect dark region will not be achieved. That is the only. So we will get the dull and bright. To get the perfect dark, what we need? Equal amplitude. So if I ask that for for very sharp contrast, we need equal amplitude. For interference, we don't need. We need equal amplitude for sharp contrast. What is contrast? A more
Light and
clear
dark.
boundary, a more clear boundary, isn't it? So contrast is a you can say mathematical term where the gradient becomes infinite, dy by dx. Okay, this is how the contrasts are developed in mathematics. So what is contrast? When a color changes sharply, we get the sense of edge. So what is the edge meaning to the brain? How brain perceives the edge? Edge of any object.
Uh-huh.
Sharp change in frequency of
No, sharp change in the,
wavelength.
yeah, you can say frequency, or you can say, yeah, the wave which you're receiving. So you can say sharp change in intensity is called contrast. So the di by dx defines contrast. So if you, let's say on a paper, if someone is doing, making a drawing, and if you want to show the edge of a building, the corners I will paint, because I'm painting, I'll make it a very sharp change. So I will take a white contrast like this. Let's say this is white. And then if I draw something here, so this edge is quite visible, although I haven't drawn other surface. But the perception of edge is clear, right? So you can see there is a line as an edge. So how the brain is able to understand this? Because you can see if you go from left to right near this region, there is a sharp change of intensity. Do you see the intensity change? From a lot of energy to no energy you're reaching, right?
Yes.
So this is the di by dx. So more as the di by dx will grow in value, you will get a better contrast. So imagine if di by dx is infinite. Okay. Or if the for change in di, dx is almost changing to. So if di is changing in a way bigger value, dx is very small. So we can create a better contrast. So the whole idea of a sharp contrast of the fringe pattern on the screen is achieved by equal amplitude. Okay. So you can just make a small note here for sharp contrast amplitude must be. So why I'm saying this? For interference, it is not required. It is required for sharp contrast. It is clear?
Yes.
So the condition for interference is done. And when two sources are said to be coherent, what is the coherent source?
When they
When the two waves coming out of the two sources at the time of emission itself
they
are having predictable phase relationship, which means they belong to almost same generation. Now this is the biggest challenge. Can we control two physical sources doing the same event? Is it possible that if you have two physical sources, speaker 1 is speaker 2, I mean not speaker, let's say you buy two LEDs and you expect that the electronic transition in the two LEDs are happening at the same time. And I'm talking about the scale of nanosecond. So on a scale of nanosecond, can we really control the two generation
No,
from
sir.
two physical source? So that is the problem.
We can.
From a
Why can't we?
physical source, we cannot create coherence. Two physical source cannot be coherent source when it comes to light emission.
Sir, any specific reason?
Because the atoms in the two sources are oscillating, exciting, de-exciting at different instant. We have no control. It's purely random phenomena.
That if we take identical, then also.
I mean, this is pure random phenomena.
Yes.
See, you have your LED, I have my LED. You have your set of atoms, I have my set of atoms. You have your own energy supply from the battery, I have my own. So can we really have the relationship the way I'm emitting the light and the way that LED is emitting the light? I mean, it's like my LED and your LED, can they have any predictable relationship?
Almost zero probability.
Because this is infinite atoms. So what is the chance that out of infinite atoms, two atoms will oscillate together? It's a
Almost.
zero probability. There is a complete randomness, and therefore the first difficulty that happened with the idea of coherent source, that we cannot have a physical source acting as coherent source, which is quite possible in case of sound. So we can have two speaker which can be coherent speaker, but two source of light cannot be coherent. So I'll put as a word. Okay, first of all, what is coherent source? So two sources are said to be coherent if their phase relationship is constant with time. Okay. The best example is the husband and wife. They have quite a different phase, but the difference is constant. So you really know that when dad is angry, what mom must be doing, and vice versa. The whole idea is they have the difference, but the difference is not changing with time. So there's quite a kind of prediction. Okay. Now, what I'm trying to say here, that two physical sources cannot be coherent in case of light. So two physical light source can't be coherent. It is impossible. That's the first thing. Okay. Unlike the sound, in sound we can have two speakers. You can buy one speaker from, if it by, let's say we have two speaker from the same company, probably the sound that they will emit will have similar phase relationship, because they don't have so much tantrum as the light. As I said, light is so much tantrum. It's so difficult. It's a delicate and very elite subject. That's why everyone is studied about it. So two physical light source can't be coherent. So we cannot expect two physical source producing the interference pattern. So we have no choice left but to take one source and split the source into two sources. Because if the split is happening from the same generation, let's say this is a group of students going for picnic, we can split in two buses. Okay, so half of the group will go in one bus, other will go in another bus, but still they are same generation. So what we are doing is we are splitting the generation. Okay, so the method to create coherent source is called splitting the generation, and the name given to it is called wavefront division method. Okay, so how to create coherent source? So methods to create coherent sources. So there are just two methods that we employ. There are just two methods. The first is called wavefront division method. The other is called amplitude division method. So when I say wavefront division, it means I take one generation and I split into two parts. So now you can understand why we call double slit. So the double slit is the generation arriving at the slit will has to go through the two parts or two routes. So some part will go from the upper slit and the other will go from the lower slit. And because they belong to the same generation, so even though they will split, the chance that they will interfere is very high. So in a way, we can achieve the task of interference. So the wavefront division method will have many names, and the one which is very famous, which is called Young's double. So YD, you can say method, or you can say experiment, which he performed. In short, we call YDSC. It is so famous, and this is the most celebrated, you can say, experiment, because this established the wave character of light, for which the Huygens suicide, because when he said wave, he faced a lot of criticism, because he need to explain something called artificial luminiferous ether. And after some time, Michelson Morley also performed the experiment, which formally establishes the wave theory. And now the wave theory is quite accepted everywhere. So YDSC is the first attempt, okay, in creating the two coherent source. Understood?
Yes, sir.
Yes.
But there are many actually. So after YDS, we have
Sir, actually,
freshness.
after
What?
doing this experiment, it was found out that electron also behaves like dual, no?
Yeah, that is also from the experiment only. The interference of the electron interference establishes the wave character of a particle, I mean physical particle. So that's why we call matter wave. The wave character exhibited by the matter is called matter wave. And as I said, the interference is the superposition phenomena, which means I'll come to the word interference in detail. What is interference exactly? But if you have some opening and if you throw the stream of electron, what do you expect? All to be accumulate here.
Yes.
But what you found is, in contrast to this, that you found as a collection of here. So how it is possible to collect things and get nothing somewhere, get all nothing, all nothing, all nothing? So this is only possible because this was possible with wave, and because the electron also exhibited the similar character. So we established the fact that, okay, even the particle can exhibit wave like character. See, it's not a wave. Don't get confused with the, I don't know what sense of wave you have. The wave like character is different from wave itself. Okay. And what is wave exactly? It's a propagation of energy, right? And momentum.
Yes, sir.
Okay. So what is happening is that the momentum given is in this direction, but we can get momentum here also. Okay, net momentum as per the conservation momentum, the net will be okay, horizontal, right? You can see all will cancel out. The vertical component gets cancelled. Anyway, the idea is when you pass through a slit, you also bend. Now, how you bend, you can explain like this. Okay, if you have a slit, if the electron is hitting this way, it will go like this. If the electron is hitting this way, it will come like this. So this way of imagine the electron like a ball getting reflected from the tiny part of slit and reaching the different part of the screen beyond the geometrical shadow or the geometrical region which you might have reached. That character we call wave-like character. I mean, how it is possible? So the wave exhibits the bending phenomena, and because the particle is also exhibiting the same phenomena, because to reach here you have to bend. So you can say, okay, they have the wave-like character. So wave-like character is important, and when I say wave-like character, it's called the probabilistic wave, not a physical wave. Probabilistic. There's so much confusion actually. So you say that if you throw the electron this way, what is the probability of achieving or receiving the electron here? Technically it is 0, but now it is non-zero. So it was non-zero for the wave, and because it is also being exhibited by the particle, so we can say it is exhibiting the wave-like character. So a wave is a delocalized idea. So when something is delocalized, then the probability of finding it everywhere will be non-zero, isn't it? Imagine something is delocalized, it is spread actually. So throughout the space in which it is spread will have some probability, isn't it? So a delocalization is called the uncertainty in the position. And if there is something uncertainty, which itself is the wave-like character, the uncertainty in the position is called wave-like character. Okay. So a wave is not found at a place, a wave is found at many places. So that is the idea of wave. Don't take wave as something like a water ripples of water and you can calling it a wave. Wave is a very much an idea. So you have to deal with the idea. So in the Einstein world, particle and wave both are ideas. A localized and delocalized idea is called wave and particle. The more you study, the more you get confused. So okay, study less.
Sir.
Yeah.
So is it like saying like classical magnets have their own magnetic field, but when we saw that a moving charge also creates something which has the same effect like a classical magnet's magnetic field. So we said that it creates a magnetic field. So saying that it's a wave-like character, is it like the same thing?
In fact, in the later investigation, we conclude that the classical magnet having the magnetic behavior because of the again charges only.
Oh,
So
okay.
eventually, it is the atom in which the electrons are moving, which is creating the whole idea of magnetic field.
Okay.
So we have the domain theory. Okay, so you can read the magnetic properties of matter, and we come to know something called domain theory, which again reestablishes the fact that it is at the end of the day, it is the moving charge. Okay.
Oh, okay.
So we have Fresnel's prism method, Fresnel's prism. We have fresh, oh, not fresh, Fresnel. This is called biprism. We have Fresnel's double mirror method, and I'm really lacking the space. So what I'll do is always remember the wave in context of quantum physics is the probability. So don't take wave as the emotion of wave. Okay, it's a purely a mathematical definition. It's a so the world of quantum is purely mathematical, and we talk about the probability of an event. So the interference, diffraction, all becomes the probabilistic event. And I'll also prove the Heisenberg uncertainty principle using the interference, I mean diffraction. So I'll prove the delta X, delta P relation, which you have studied in the later chapter. So we have the fourth method. Okay, I'll just repeat here. Lyot's single mirror method. So these are the famous one. Then we have something which we have developed, like we as a lab experiment. So we have cutting of lens, and then we have something called modified YDSE. So we'll talk about how we can, modify the situation and get a different kind of pattern. So all these things we will study in detail, and then so many things. Let's go to the 7th ETC. Now in the amplitude division method, so we have very famous, which we all observe, called thin film interference. So when you see the feather of the peacock, you must have seen a nice color pattern. Have you seen the pattern of color?
Yes.
Yes.
That pattern is called the diffraction grating of the feather. So actually it is not a pattern. When the light is hitting the feather, because of the molecular gap in the feather structure, the light is getting diffracted and forming a round shape with some superposition part. That is why you see the spread of light in a beautiful pattern. So most of the colorful feather is the result of diffraction, especially the butterfly. So the butterfly will show you different pattern from the different angle also. And that very much inspired us to create the currency notes. So we try to incorporate as much diffraction and interference as much possible to kind of prevent the duplicacy of currency. So some currencies are really expensive in context of a world economy. So they undergo a very tight, set of event. So they use different ink composition, different color composition, and different material to develop close to the interference and diffraction pattern as exhibited by the butterfly, because the more complex the phenomena to generate that currency, more difficult to replicate, and they can stop the fake currency market. It's a big problem for the world economy. Anyway, so we have thin film interference, which you generally see during the rainy season. If you see, the roads will have a nice colorful pattern. Have you seen that? So when the automobile, when they leak out of the vehicle, it spreads over the water as a thin film.
For some time.
Yeah, and when the light will hit that layer of automobile, different color of white light, because white light is a composition of different color, they create their own pattern of diffraction, which as a whole looks like a really nice colorful pattern. So those things are called thin film interference actually. Diffraction and interference are loosely bounded. There's not much difference. Mathematically, no difference. Difference is the context. Okay, I'll come to that also. So we have another thing called air wedge. So we take two glass slides, the slab you can say, and we put one glass over the other with one of the edge slightly lifted. And to lift the edge, you know what we do? How to lift the edge? By putting some object, correct?
Yes, sir.
So what we put is called the hair strand. We take one hair strand, we put it there. Imagine the lift. Technically, you won't be able to see it actually, because the lift is only due to the one hair strand. But that tiny gap will at least preserve the coherence length property. And therefore, you can again see the interference. If you lift by large value, again, you won't be able to see the interference. So we have air wedge, we have Newton's ring, So Newton's ring is particularly important for the when you go to the BTech first semester in the physics lab, you have to perform this experiment for sure. The Newton's ring. I'll give you all the theoretical background of every phenomenon. So what I'll do is I'll again start from some of the more basic thing. So next lecture will be again purely theoretical. Probably after one lecture you will start solving question. So the theory will expand for some more time, and we'll come back to the problem solving after one more lecture. So it's quite a deep theory. So we have to study the entire Huygens principle separately. We'll study how the wavefront method we can achieve the laws of reflection, the laws of refraction, and then we can come to the actual chapter. Okay. So I
Yes.
hope the theory part is clear. Like you understood what is the concept of wave,
Yes, sir.
the meaning of phase, because the phase idea is very, very important. And what we really do is we see the superposition is basically addition of two vectors. It's as simple as that. So when you say the superposition, when you say interference, you say the same thing. At the core of all, we are trying to add two vectors. So imagine if I give you some simple logic, you can tell me the answer directly. Something really simple. I'll end the lecture because we have another lecture after some time. If we have two vectors of same length, let's say E naught, and they have same direction, what is the resultant value? Now, if I say the intensity of each is I naught and I naught, what will be the intensity here?
I not. Oops.
Because I naught intensity is always
Amplitude.
proportional to square of the amplitude. So I can say the intensity of the each individual component is proportional to. So I naught is some constant into E naught square.
Yes, sir.
So the IR will be proportional to 2E naught whole square. So IR will be equals to 4K E naught square, isn't it?
Yes, sir.
And by definition, because we call Ke naught square as I naught, so you can see clearly the IR becomes. So what we are trying to understand that when you add a vector, the intensity behave quite differently. So the two intensity, although scalar, it's very interesting. You're adding two scalar. So when they get added together by virtue of the vector, the I1 plus I2 is not I resultant, rather it is different from I resultant. So what is I resultant? It is more than sum. Okay. And imagine if we have two vectors which are coming at a point in the out of phase fashion. So one is coming as a crest, other is coming as a trough. So what do you expect the IR? So what do you expect here?
0.
The ER is 0. So I is 0. And that's why I said if we have two source, so they are same generation, but one is taller, other is smaller. So now the resultant is how much?
10 minus 20.
So the IR will be proportional to. So basically you can see IR will be equals to. So that is why I'm saying that the intensity will be non-zero, and that will not create a good contrast. So the sharp contrast will be missing. At the end of all this chapter, what we are going to do is only adding vectors. So we are going to learn how to add vectors. So I hope you all know the triangle law.
Ah,
If
sir.
you don't know, please revise because we are going to use it extensively in this chapter. Okay. Bye and take care. See you in the next lecture.
Thank you, sir. Bye, sir.
Bye, sir.